Going to 83. Here's the two techniques. Yesterday we did method of comparing coefficients, right? Today we do everything else, so juggling with other things. All right, the method of comparing. So do you believe that it works all the time? It's very consistent. Multiply the denominator, look at the numerator, you can compare the coefficients. Although it's tedious and it works all the time. All right. The reason it works all the time is because of what theorem? Why is this 4 by 4 or 5 by 5 equal? Why is it always solvable? Right, Bezout's theorem says that it always is possible, therefore it must have a solution, right? And by looking at an equation, it's difficult to conclude, actually. It's an interesting part. So second technique is a method of specialization and reduction. There's no consistency in here. You look at it here, feel like this is better, and you do that, and hopefully you pick that up going through this various technique. So try to avoid that computate the coefficient technique, right? So let's begin with this one in here. The same thing. We're doing the second method. That's what we're doing. Right, I'm going to call this one a linear and quadratic case. Linear times a quadratic. Still works even the quadratic is not irreducible. If this is reducible, such as x squared minus 1, I think technique still works. It's not really necessarily using the quadratic. The idea is the following. If it is small like this, you cannot further reduce it like this. What is the degree of the denominator? 3, right? If I put degree 2 up here, that is the condition that Bezout's theorem, Bezout's identity applies, right? But you can use the other two factors to knock down those things. So that's what I mean by reduction. One is the smallest degree it gets. You cannot reduce the numerator any further. So this is the fundamental case. So here's the thing. You write the quadratic here and use this L to divide the other quadratic. So L times the quotient. I already used Q, so I use something else. Do you expect this remainder to be a constant because your divisor is a linear? Does that make sense? This is your divisor. So let's do that. This is not x squared plus 1. And what is a linear? X plus 1, right? And what is the, do you see that quotient quickly? You do the long division. Must be quadratic. You've got to match that x squared there. And it does not have linear term, right? So we've got to cancel that linear term. It turns out -1. Then it's -2, -1. It must be 2. So that altogether works out +1. How do you get this equation? Again, long division. If you divide this polynomial by x plus 1, long division, that's the quotient, and that's the remainder, right? So it turns out this is always consistent like this, x squared plus 1 minus the linear. Whenever there's linear and quadratic, this method works really nicely, like that, and it is equal to 2. Make sense? Now you divide the LQ, then it enters very nice form. So if I divide this one by LQ, so that's Q minus LH equals to 2, and I divide everything by LQ, everything by LQ. Is that right? So what happened? Left-hand side, 1 over L happened to be the decomposed form, minus L cancels, and H divided by Q. Q is a quadratic, and H is x minus 1, equals 2 times LQ, right? So do you realize that this is actually the decomposition, partial fraction decomposition? Constant divided by linear, linear divided by quadratic happen to be the case, right? Whenever there's quadratic and linear involved, this technique turns out gives you a very quick answer. If it gets more complicated than this, there's no easy answer. It's just that low degree like this, there's a better method than comparing the coefficients. So what is it we have here? 1 divided by L, which is x plus 1, minus, what is H? X minus 1, the quotient, and the quadratic equals to 2 divided by LQ. L is x plus 1, Q is x squared plus 1. Does that make sense? But that's not supposed to be 2. It's supposed to be what? 1, right? So how can you make that 1? Divide everything by 2, right? So that's exactly why we had using the coefficient method, right? No solving an equation, more of an algorithmic, and you get to the answer. So here is the final answer. Because of uniqueness, we arrived the same answer. That a up there is 1/2, and here is 1/2 x if you liked this notation better. But you can put that 2 in the denominator. That's the decomposition of 1 over LQ. Does that make sense? Any question about this method? Whenever there's LQ involved, consider this one, and so something nice falls out of that. Right? Make sense? So here's a reduction. We have the same denominator there, right? Same denominator. Numerator is a little bit more complicated. How can you do this thing? And this is what I mean by, if the numerator has a degree like that, it's a little bit more than constant, we can kind of take care of the numerator there. All right, so here is what we're going to do. Here's L, and here's a Q. I find it is very time-saving if you use LQ instead of all that. So can you reduce x squared minus x plus 1 kind of divided by, well, I'd like to use x squared x squared plus 1 is a higher degree. So do you see that x squared plus 1 is kind of already in there? Yeah? And minus x, right? So this is something, if you divide the numerator by q, that's going to be the divisor. Quotient is going to be 1. Remainder is going to be -6. This rearrangement is like this. Sometimes it's not easy to see it. Then you actually have to divide the numerator by that q and rewrite it like this. Now here's x in there, but we have a still linear factor. So we can still write that x as an x plus 1, don't you think? Then it nicely cancels with L. You see that? But it has to be equal to the before, so there wasn't any -1 before, but it's a positive 1, so what should I put here? 2. Then altogether it remains the same. The good thing is that this time it has q in it, that time has L in it. So when you split it, it becomes, this is q and that's L. Do you see how that's split? When you split it, it's 1 over L. When you split this one, LL cancel, minus 1 over q. And you're left with a 2 over LQ. Correct? So isn't that already decomposed form? Degree less than q, degree less than L. And this one, we just did it, right? 2 over LQ. And then, yeah, you just do that one in here. So it's 1 over L minus h over q. That's 2 over L. And there's one more 1 over L minus 1 over q plus. That is this one. So altogether is a 2 over L minus altogether h plus 1 over q. So 2 over x plus 1 minus, what is h? Was x minus 1, I think. H was x minus 1. It's x minus 1 plus 1 is x, and x squared plus 1. That's a decomposed form. Each of them is irreducible factor, and numerator less than that. Does that make sense? So that's one juggling method. The second method I was talking about, if it involves L and Q there. So L and Q, it is based on this fact, and you can handle the coefficient. That case. Another one. So it is written here. So those are denominator being two simple irreducible factor. Simple means each of the factor is not raised to a second power, third power. There's our first power there, right? One irreducible factor raised to first power, another irreducible factor to the first power. So that's what we mean by simple irreducible factor. If this gets higher power, it gets more complicated, and that's next group. All right. This one is also a bit tricky. It's quadratic times quadratic, right? So let me see that. It's supposed to. So how is this supposed to split? Here's a 2x squared plus x plus 1 plus 3x squared minus x plus 1. According to the Bezoos identity, if you believe these two are irreducible, right? You have to check that one. You can't assume it is like this. If it's irreducible, then you don't have to consider what factors involved. It's irreducible. So hope you see these are irreducible, both. Then there's no common factor, right? If it's reducible, maybe there is a hidden common factor. You can't split it like this. But once you split like this, what is the numerator supposed to be? Degree less than the degree of the denominator. So it's ax plus b, cx plus d, right? And coefficient gives you 4x4 equations, right? But if the goal is getting down to low coefficient like this, and it's still, if I have instead of 1, if I have x plus 1, it still works. If you have x squared plus 1, you can reduce that using one of the factor. So get down to degree 1 level. Numerator is 1, at worst is degree 1. If you multiply this one out, they must cancel out, right? They must cancel out such that these, when you cross and multiply, and I hope you get that one, the higher degree ones. So if you, for example, if you multiply these two, and you have degree 3 and degree 3, that should go, right? Because eventually there's no degree 3. Okay, so it's a lot of inspection and juggling to get down to the answer. So I think it's my natural choice that, okay, if I have to kill that degree 3 term across it here, I would put, for cancellation, I will usually put a negative there. The leading coefficient here multiplied, leading coefficient multiplied there, they must cancel out. So what should I multiply to 3? What should I multiply to 2 so that they cancel out? My natural choice is that, okay, I'm going to do 2x plus a and 3x plus b, such that 2 times 3, their degree 3 part cancel out. So that's my first choice I will try. By doing that, I reduce it to a and b, 2 variables, much better, right, than 4 variable to play with. All right. So what happens to the numerator now? Numerator 1 is supposed to be equal to 2x plus a, 3x squared minus x plus 1, minus 3x plus b, 2x squared plus x plus 1. Right? If you multiply the entire denominator, q1 and q2 both sides, left-hand side becomes 1, and q1 cancel, and q2 is multiplied there, q2 cancel, q1 is multiplied there. Agree that's going to be the numerator level if you simplify? This should be always true, and you have to compare the coefficients and all that, right? So I think it should work out. I think I should have think a bit more careful. But let's see. If what I'm saying is that I might not be able to match that 1, then later all I have to do is just scale it a little bit. But if it is a constant or linear, we can still use that, and you have to just scale it later on a little bit. All right. So if this works out, so let's compare the coefficients. So the square is gone, cubic part is gone. Can you collect the squares? I see 3a, right? And this is negative 2. So okay, this is all I get from here. 3a squared, and x times x, that's negative 2. That's the coefficient of x squared. What do you get from here? X squared is 2b, but it's negative 2b. And these two will give you the coefficient. What is it? 3. Positive 3, but it's a negative 3. So that's inside of x squared, right? Correct? How about the other one? X. What kind of coefficient you get from x? I see a 2 here. and I see negative a. I think that's it, right? What about here? Minus b and plus 3 and minus 3. Is that right? Correct? Did I do this right? 2, 3 there, and b. And plus whatever is left. A minus b. Correct? So if this is a constant, and I'm going to put and this one 0 and that one 0, from there I get a and b. Right? Because two equations. It's a lot simpler than 4x4 equation. Then I don't have a control on that one, a minus b. Right? Once this is determinant AB, I don't have a control on that one. But if this turns out 5 or something, and then I can divide everything by 1/5 to get to that 1. All right, so let's solve this one. So this one in here is a 3a minus 2b equals 5. Is that right? If this is set to be 0, because it all has to be constant polynomial. How about the other one? A plus b must be negative 1, don't you think? Negative 1. This is 0, so a plus b is a negative 1. So 3a minus 2b is a positive 5. So do you see the solution? 2a, 2b equal negative 2. Then if you add this 2, I have 5a equals 3. So it seems like a is a 3 over 5. Correct? And b, if it is a 3 over 5, negative 3 over 5 minus 1, so b is negative 8 over 5. So if you subtract these two, what do you get? 11, a minus b over, this is 11 over 5. Okay? So what do you get here is that a is a 3 over 5. Was that 2x? 2xa. That's 3 over 5, and q1 there, minus 3x, b is negative 8 over 5, and q2. If you do that, all together is q1 and q2. Then we have these two things controlled, and the rest of the part is 11 over 5. That's the decomposition we get. We want 1 over there instead of 11 over 5, so you multiply 5 over 11. So here, 5 over 11 multiplied, 2x plus 3 over 5, q1, that's the decomposition, and 5 over 11 multiplied, 3x minus 8 over 5, q2 multiplied, that now becomes 1. Now you get q1, q2 factorization. Okay? Hope that makes sense. So general case, you have to reduce and things like that. So if quadratic factors are involved, you need a little bit of trick if you want to avoid the bigger size of a system of equation. And these are the two tricks that I introduced. First one was easier, using long division. Second one was a bit harder. But think about entering 4x4. This could be a lot quicker and more convincing. Right? Yes.
Will we ever have something with more than 4x4, or is that the worst you'll ever get?
I think there will be one case with 5x5. But I'm going to introduce a trick that uses this one and long division trick, and it's really quick. But it is in the book problem, so that's why I'm doing this. So if you do approach that, and you will enter 5x5, and that's horrible to solve 5x5, but long division gets you there really quickly. But you agree that the example we've been looking at here so far, all two simple factors. Quadratic, quadratic, linear, quadratic, linear, linear. Right? Those are the two simple factors that I've introduced in there. So one more, the technique I'd like to introduce is the specialization that I haven't showed you there. So going back to the earlier example like this one. So this is easiest technique, then students usually like this one a lot. This is another two simple factor. That's another example. All right, how does that factor? 2 divided by x minus 4, x plus 2. Now this right? And then this one is supposed to decompose like this. Is that right? Going to the Bezoos identity, they're all irreducible, have no common factor. It's supposed like this. It's not polynomial, it's a constant because denominator is degree 1. So if you look at this one and compare, you see that you enter this equation 2 equals a times x plus 2, b times x minus 4. You agree? And then we compare the coefficients, right? So I'm introducing a new technique. Bezoos identity says that this is always possible. All you have to figure out is this a and b. So if that's so, specialization works really nicely. So here's one. You look at these factors and try to make those factors 0. It turns out it's really easy to do that. So how do you make this factor 0? Plug in what value? X equals -2. So left-hand side is identity, so it remains 2. There's no x in the left-hand side. Right-hand side becomes 0 plus, if I plug in -2 there, what do you get? -6b. Is that right? Is this right? -6b. So what is b here? -1/3? Right? Yeah, that's what b should be. What is the second specialization we have to do? X equals 4. Make that factor 0. So plug in 4 there. Then left-hand side, no x in there, still 2. This one is 0 now. If I plug in 4 there, I get 6a, right? So what is a? 1/3. So I got a and b really quick by just plugging a couple of values. This is called specialization. The idea is by making complicated terms 0. That's the idea. So what is the decomposition? Here's a L1 and L2. This is representing this factor and that factor. And up there, 1/3, L1, -1/3, L2. That's done. That's a specialization technique. This is one of the secondary one that I was talking about here. Reduction in numerator and specialization was something we just did. Differentiation we haven't done yet. So all these things combined just to reduce the amount of calculation. That's all that is. If there's a repeated solution, there's everywhere x minus 1 repeated, and then specialization reached the limit, then you have to differentiate. Right, you will make everything 0, hiding. So here it's nicely isolating. When I plug in x, this one survives. When I plug in that one survives, right? But if there are too many things, it kills everything, and then you have to differentiate. But there are other roads than differentiating, so that's one thing. So let's see if we have summarize two simple factor case nicely. Before I do that, we enter three simple cases. So maybe I should introduce this example. Everybody knows the answer to the antiderivative of secant x, right? What was that? Antiderivative of secant x? Natural log of secant x plus tangent x. That's the answer. And their answer is like cheating. They already know the answer and pretend they discovered this weird. So this is one reasonable approach. Here, okay, if you play with the tangent secant, you realize that you use substitution, keep circling back to itself. So I decided to enter, if I really have to do it, let me just look at it this way and see if I can do the u substitution in terms of sine and cosine. If in u substitution works, you want to have some sign up there, right? Sign up there. But here's one algebraic technique you might think of. If I multiply over there, then there is cosine x. So u is a sine, and then that cosine will cancel, right? And cosine squared, it's not bad. Pythagorean identity, right? What happened? 1 minus sine squared x and cosine x. If this one appeared in exercise set, everybody knows what to do with this problem, right? What did everybody say? U equals Sine t, sine x. Then u substitution works, right? Reciprocal cancels the cosine x, so how does it enter? 1 minus u squared cosine cancel, and that changed to du, right? Now you enter partial fraction decomposition, correct? So if you're more comfortable with the u squared up here like this, you can change the sign like that. And what is the first thing we have to do to decompose? So here is the fractional part, u squared minus 1. I set aside the negative out there. So what do you do first? Is u squared minus reducible or irreducible? Reducible, right? U squared minus 1. How does that reduce? U minus 1 and u plus 1. All right. Then this is the position of partial fraction decomposition like that, right? You know the coefficients? Coefficients? 1, 1, is that right? Now if you subtract that, u plus 1 is 2. I think there's 1/2. The thing that we just did, a and b, and specialize, and I skipped that step and arrived at use of partial fraction decomposition. So skipped. Usually you do partial fraction decomposition here, right? So you arrive at here. So let's integrate. Negative 1 over u squared minus du is a negative of that one in here, right? 1/2 factored out. Negative out there, 1/2. 1 over u minus 1 minus 1 over u plus 1 du, right? So what is the antiderivative of 1 over u minus 1? ln absolute value of u minus 1, right? Plus or minus ln absolute value of u plus 1 plus c. Correct? And then there is negative 1/2. Then what happens? ln together is the absolute value of u minus 1 and u plus 1. Is that right? Because it's ln of something minus that. So it's plus c. So that's the u substitution result. Now you have to substitute it back. What do you have there? Negative 1/2 of ln of, what is u? I think u was cosine was a sine x. With a sine x. Minus 1 and sine x plus 1. All right, that looks a little different from what we know about the answer, but it's supposed to be the same, right? Because of what theorem? Uniqueness of antiderivative. It doesn't matter how you do it, they're supposed to be the same. If you sketch the graph of this one, it's supposed to be exactly equal to ln secant and all that. So how are we going to enter the secant thing? And also, there's no square root of 1/2 in our formula, ln secant plus tangent. So some squares are pulled out here, I think. So I think we have to multiply. I don't know which one is right one. I'm going to multiply 1 sine x squared plus 1 in both top and bottom. So here is the sine x minus 1, sine x plus 1. So you multiply sine x plus 1, sine x plus 1, and that changes to, I may change my mind, there, negative 1 there. That changes to cosine squared, right, if you multiply them out. So here's a negative cosine squared. And what about this one? It's a square, so it's a sine x minus 1 squared. Right? If you multiply that, and denominator change to cosine squared, numerator change to perfect square. So that takes care of this negative 1/2 business there. So here's a negative ln absolute value. That 1/2 becomes a square root, becomes a sine x minus 1. That becomes just a cosine x in there, like that, right? And then here is negative ln. So what is a sine x divided by cosine x? That's known as a tangent x. minus this one known as the secant x there, right? 1/2 is inside this ln becomes a square root. So now inside is now perfect square. So the square root over there inside ln cancels this square, becoming just this sine x minus 1 without square, cosine x minus 1 without square, right? I realized that I did it wrong, so I have to take the reciprocal again. So now negative 1 goes inside there as a reciprocal. It's ln of 1 over tangent x minus secant x there, right? That's a reciprocal. But tangent x squared minus secant squared x, that is, or the other way around, secant squared x minus tangent x squared, that's 1, right? Because of identity. So if I multiply positive version, I can flip this one like this, because they're all inside the absolute value. You can just change the sign whenever you want. So if I multiply secant minus tangent x there and the secant plus tangent x there, denominator and numerator, then what happens is that ln becomes down there is a secant squared x minus tangent x. Up there now secant squared x plus tangent x. And now this is minus with a minus, that's a 1. So finally we enter ln of secant x and tangent x. And I was saying this is a more reasonable approach than whatever they have it in the book. Okay? So what I did is simple. It's just a lot of trigonometric algebra to get to the shape they want. Yeah. All right, so that's the answer, and that's the algebraic work. All right, that's one example. Still, we're in the 2 factors. Now we're entering 3 simple factors, right? And the specialization technique really becoming powerful in here. So before we enter that, let's look at the Bezout's identity once again. Bezout's identity was about 2 factors, right? Now I throw in distinct 3 irreducible factors. They're all distinct, no common factors. You can write it as 3 factors. They don't have mutually any common factors. But Bezout's identity applied 2 times allows you to split all like that. Okay, it's not too hard to show that. So, for example, if you start with a p divided by p1 and p2 and p3, right? You can group it like this. p1 and p3, they never have a common factor. So p1 and p2 times p3, they don't have a common factor either, because across it there's no common factor. So according to that Bezout's identity, you can split it r1 prime p1, r2 prime p2 p3, right? According to the Bezout's identity, correct? And then you can apply the Bezout's identity here one more time. Then it's going to become r1 prime p1, where the degree of that one is smaller than p1. And here, degree of r2 is smaller than degree of p2 times p3. And apply that identity, you arrive at r2 p2 plus r3 p3. So, one at a time, you apply Bezout's identity, you arrive at here. Okay? Is extended version make sense? Another key important thing is that when you split it like this, decomposition, the key important property, the degree of the numerator is all less than the degree of an irreducible factor. Not the degree of a denominator. That's probably one thing that you have to cling on to. Not just the degree of the denominator, but the degree of the irreducible factor of the denominator. Right now it's the same thing if it is p1, p2, p3 are all irreducible factor. All right? But you start with a smaller degree in there, and that is unique and so on. So let's see if we have examples. So setting up, that's the beginning. So do you see that's the 3 factors there? X factored out, x squared minus 16. So let's start with this one. So this is a 3-factor case. Simple. That means there's no 2 copies of a same irreducible factor involved in there. All right, so you see factorization. X is factored out, right? Common factor, x squared minus 16. And there's x squared. Ready? So why don't I change that to 1, because I don't want to see this cancel out, right? And then becomes two-factor case. So why don't I change the problem to more interesting, like this, 1. Then further it factors x and x minus 4 and x plus 4. Now, those are all irreducible factor, and they're all different, right? Correct? All right, how does that split? Irreducible factor down there, another irreducible factor down there, another irreducible factor down there. That Bezout's identity guarantees that it factors like this. And how is the numerator? 1 degree less than the irreducible factor of the denominator. That's the key. So they're all constant because denominator is degree 1, right? So let's enter numerator equation. After you multiply entire denominator both sides, left-hand side becomes 1. What is multiplied to a? X minus 4, x plus 4. Is that right? That's what's going to be multiplied to a part. How about b? X and x plus 4. That's what's going to multiply to that. How about c? X times x minus 4, right? Now your goal is that this is a polynomial, okay, you have to figure out what ABC is. So you're going to enter 3 by 3 equation or what? There's a better method, right? What is that called? Specialization. So what is the first thing you're going to put in there? Zero is some sec available. That knocks these two down, right? X equals 0, x equals 0. Correct? So what's left-hand side? Always 1. There could be x involved. Then you actually have to plug in x equals 0 there, right? But what if it is this one here? 1, 0 is a 4. Is it negative 16a? Is that right? The 0 and 0. So what's a value here? Negative 1/16. That's what that a is. Brilliant. X equals next value? 4, right? That 4 kills this one, and that kills that one, leaving only the middle part. So left-hand side, no x is in there, still 1. Middle one survives. So 4 times b times, what is this one here? 8, right? So what is b? 1/32. Okay. How about c? What do you multiply in there? X equals negative 4. Then this kills that, and that kills that. Left-hand side is still 1, so that's negative 4c, so times negative 8, right? So what is c? Still positive 1/3. So I got this ABC really quickly. No sweat, right? Make sense? It's very nice. If there's this linear factor like this, specialization is really, really nice. Even there's a multiple factors like x minus 4 squared, and you still can do that after you differentiate, and it still works very nicely. If you have x minus 4 raised to second power instead of x there, let's say we don't have x in there, x minus 4 second power x plus 4, then you will have x minus 4 here and x minus 4 squared. So by plugging x minus 4, you always kill 2 terms. So if you differentiate one time, then 1 powers of x minus 4 disappears, and if you plug in x minus 4, x equals 4 there, that one now survives. Before x minus 4 disappeared. If you differentiate, that a survives. So you can pull out still nice thing. If they're too long, differentiation gets a lot of terms, but still sometimes it wins against other method. Right. Yeah. If there's irreducible quadratic factors involved, that makes it still very complicated. My LQ method, dividing Q with L, this seems like the fastest one. All right, there is the 3 factors in there, right? And you can also try that, the same idea, but you can reduce it, but that doesn't necessarily speed up the time because specialization works really quickly. So I will just do that one time and take care of that. I think all these examples in here, they're all simple 3 linear factor. So specialization works really nicely. Okay? Does that make sense? All right. So let's see if I have another example. So I try to summarize it here. Simple irreducible factors, 2 linear factors, What is the fastest method for that? 2 linear factor in the denominator. Specialization, I think, is the best one, right? If it's 3 linear factor, still specialization is the best one. L1, L2, LQ, I don't think I have considered it yet. The 3 linear factor is a bit complicated. L times Q, that's one thing I did with using the long division. It seems like that's the fastest way to do it. So no specialization, no comparing the coefficient. Divide Q and L, and there's a nice way to do it. Q1, Q2 is the one that I did with 2x squared plus x plus 1. So kill that leading coefficient first, and usually you get a very nice information. You can tweak that result to get something. All right. So these cases are hard. LQ, Q1, Q2, L1, L2, LQ. Those cases, specialization, comparing coefficient, they're all give you a very long answer, and slightly different thing was introduced there. Okay. All right. Oh, sure. So this part is about when there are repeating factors applying in there. It's not all different. Not P1, P2, P3. They're P1, P2, P3. They're all equal to P. So we have repeated factor appearing there, right? Then using the long division process, which is our AP problem at the moment, and you can write it like this, using the long division process, right? So I encourage you to actually do that on your own. Bezoos identity is pretty difficult. If you'd like to challenge yourself, because you like mathematics, and especially in this level of mathematics, you can try your Bezoos identity on your own, but it's a pretty, I don't know, it's a clever idea that's involved in it. Long division is not, this is not that hard. So although it's an advanced problem right now, I think it's something doable. All right? So I think it was running out of time, so I'll stop it here, except I'm going to say one more word about. So tomorrow we're going to do examples with a repeated factor there, but today is all distinct factor. We did that. Only thing I didn't do is this L1 and L2 and Q, right? One linear factor, another linear factor, and a quadratic. So let's consider, I don't remember how to do that one, so let's consider quickly. Last, no repeated factor there. Okay, so for example, if I have x minus 1, x plus 1, and x squared plus 1. Like that. Oh, this is a good example of a specialization. I think that's what I had in mind. So this one splits in what way, you think? X minus A, and x plus 1, B, and how about x squared plus 1 up there? Right, it has to be 1 degree less, so it's a cx plus d. Correct? So let's do that. It's 1 is equal to what? A is multiplied by x plus 1, x squared plus 1. B is multiplied by x minus 1, x squared plus 1. And c is multiplied by, not c, but cx plus d, multiplied by x minus 1, x plus 1. Is that right? I hope I did this one right. So from there you have 4 by 4 equations, right? But is a specialization available? Available here, and 1 and negative 1. So 2 value, it's available. By doing that, I think we're going to get nice values. So let's try x equals 1 there. What do you get? Left hand side is still 1. 1 kills that one, 1 kills that one, so we're leaving only a. That's nice. So is it 2 times, is that 4 times a? So a is 1/4. We got a. How about x equals negative 1? Left hand side is 1. Negative 1 kills that. Negative 1 kills that. So it leaves that. Negative 2. Negative 1 is negative 4b. Is that right? Negative 2, positive 2, negative 4b. So b is what? Negative 1/4. Correct? Now we run out of this specialization, and then you have to figure out still C and D, right? Correct? So here's my idea. Why don't you keep plugging in since you're just left with C and D, right? What is the simplest number you can try here? Maybe 0? 0 is not going to kill anything, but we already know A and B pretty much, right? So if I plug in 0, it should still work, and 0 is 1. What if there's 0 there? A is 1/4. 0, 0, that's 1, 1, correct? B is negative 1/4. If I plug in 0, that's negative 1. 0, that's 1. If I plug in 0 here, now that kills the 0. That's very nice. It's isolate D there. And 0, 0, that's negative 1, right? Well, that gives you what D is, right? Correct? Yeah, so what is D here? Negative D, so that together is 1/2. Negative, I think it's 1/2. Do you agree? That is positive 1/4, together 1/2. Subtracted it is a positive 1/2, negative, so it's a negative 1/2, I think. All right, negative 1/2. So I got D. How about C? How are you going to get C? Plug in something else, but it becomes like 2, then it raises to 5. That's not too bad, right? That's not too bad. Dealing with the 5 is not too bad. So I will try x equals 2. Why not? And then that'll tell you what C is. But when you reach 2, it gets too big or something like that, and then you may consider something else, like differentiate this whole thing. But every time you differentiate, you have 4 terms come out, 4 terms come out. So it's not necessarily the best way. I would play with x equals 2 to get what C is. All right? So that's the specialization. That's kind of circumvent the comparing the coefficient, which you require correct algebraic work, but simplification, algebra work with the numbers, that's a slightly smaller chance than you make mistake when you're collecting that. So those are altogether what kind of situation? Simple irreducible factors. There's no repeated x minus 1, x minus 1 squared that didn't appear. They're all different irreducible factor. These are the kind of the basic case, and we know how to do that, especially that specialization. Okay, so today when you do this, especially pay attention to this L times Q and try to use different method, speed up. Think about I'm in the test situation. If I compare the coefficient, wow, it takes too long. What am I going to do? Maybe you're going to consider that long division method I showed you. LHQ, that method. All right, I'll see you tomorrow.